Hello. So in this first lecture, I will begin with the more philosophical underpinnings of open source software, tying that into GIS, and then providing some specific examples. The term open source software was coined by Eric Raymond in 1998. And I say here he thought the term free would be misunderstood. There's connotations of, a good deal, cheap maybe with free. And open source software is maybe more intensive to learn how to use and to develop than other software applications. And so that term, free, was not something that he wanted to characterize the movement. And so instead, open source. So this made reference to the source code of software, this being vital to the operation of the software, and also parceled with a bundle of other rights for use and for development that had been typically, and are still largely, reserved for the copyright holders. So open source software. So this is provided under a license that permits users to use, change, and improve the software and to redistribute it in modified or unmodified forms. It's openly developed in a public collaborative manner, but that doesn't necessarily restrict onward uses of it. For example, we'll see in GIS how many proprietary softwares and platforms make use of developments that were developed openly. So what does open source entail? Here, the free redistribution. So the software itself can be shared, and anyone who receives it legally can use it without payment. And the source code itself needs to be distributable as well, whether or not that's kind of the default in how the application is distributed, or something that kind of entails an additional request or kind of steps for access. It's something that is possible. Not to say that it's necessary. So derived works, this kind of makes reference to the modification of software, so that these are also something that are allowed. And it can be named differently, and in certain cases has to be named differently, such as if the rights to use of that product are restricted, would need to be named differently from the original source code, original software. So there can be no discrimination against persons or groups or fields of endeavor. So again, somewhere where the term free might be relevant, might be applicable, but also one that wishes to avoid any kind of confusion that could be generated out of that. Free software, on the other hand, is a thing, and this is kind of generated maybe by a parallel but distinct line. Here, Richard Stallman is implying that free in this movement is meant as in freedom of speech, not free as in free beer. And here this makes reference to the same kind of potential confusion where free isn't meant to connote cheap or easy, but rather the universality, the wide applicability, and almost or nearly unrestricted access to the software itself. So the four freedoms marked by free are the freedom to run program for any purpose, the freedom to study how the program works and to change it to make it do what you wish. So this also kind of implies access to the source code, not just to the user interface of an application. The freedom to redistribute copies so you can help your neighbor, and the freedom to improve the program and release your improvements to the public so that the whole community benefits. So we talk about licenses. Licenses are the ways in which users are given rights. So for example, certain licenses allow for free use of the product at hand. These can or cannot allow for derivative products to be restricted or not. So some terms here: open source versus free software. It's distinct parallel lineages, somewhat overlapping in what they're referring to, but the focus might be different. So use of open source focuses on the strength of peer-to-peer development, so kind of a decentralized, somewhat open development model, and with specific reference to source code. Whereas free software is a focus on these philosophical freedoms. Again, mostly overlapping. And in fact, free and open source software, FOSS, is an inclusive term that's often used. And in fact is used in kind of the name of the premier in-person conference for development for these. Other terms that you might hear but are not maybe necessarily underlying what this course is about are freeware. So this is software that's available freely but not necessarily the source code. Closed source. So this is, I might often talk about commercial software, proprietary software. Open standard and open data, we might get into this a little. So open data are data where the values within a database available to everybody. At a base, that means available for people to use. It can also mean available for people to contribute to. Open standards are ways that data, I lost it, are ways that data can be structured. Kind of what kind of values are stored there. How many values, what their data type is. Is it a number? Is it a string? Is it a date, for example? And kind of how those values are communicated. So one example, not of an open standard, but on any kind of standard is how do you communicate position on the Earth? And so in a geographical coordinate system, that would be angular measurements of latitude and longitude. How are those represented? Oftentimes within parentheses, separated by a comma. You find values of latitude between -90 and 90, longitude -180 to +180. So these are just standards. And open standards can communicate much more than just geographic data, but it's a way for them to be read. In this slide, there's a comparison of the development cycles between proprietary, commercial, closed source, and open source software development. So the first might be just the objective. Proprietary, that's to maximize profits on sales. For open source, it's creating a stable software that solves a problem. Oftentimes there isn't a profit motive, and rather it's people who are hobbyists or just very interested in the employment of the software, the use of the software, and so want to make it better. There's less of a distinction in open source between the end user and developer. That's not to say that there's no distinctions. I mean, in this course, we'll become end users of a lot of different applications and standards where we won't really develop those themselves. So we may create products using them, but there's kind of a user base and a developer base. But it's one that's open. So if you are incredibly interested in this, you might kind of go on to develop and to contribute to these. It's open. You don't need to get hired to do it. You can't just start tomorrow, I guess, but the boundaries are more porous, and they're certainly different. Whereas in proprietary software, there's kind of a corporate structure for planning and development. users could be customers. There could be also kind of structures for beta testing. And the cycles for release of new products are based on a marketing plan, a business plan. And that's not to be kind of cynical of, say they're holding things back from you, quality, kind of planned obsolescence things. But there would be kind of gaps or periods of time where functionality that has been developed by the company has not yet been released, whether or not that's due to insufficient testing in their eyes, or just due to a desire to kind of package a bundle of updates together as a version. So in open source, it's possible because more people are working on more things in a decentralized manner for these fixes to get out quickly. So it's not maybe as streamlined as when there's kind of a new annual update. Things can happen much more quicker. Let's see, and so this stable release, there's a lot fewer releases for these proprietary platforms compared to open source. In open source, I said it's maybe driven more by the interests, hobbies, passions of a kind of community. And so as long as it's useful, it'll go on. That's true and it isn't. I mean, certain projects can be thriving when you compare it to maybe other projects, or maybe even the same project at a different moment in time. You know, who's going to find it useful? Potentially, it's a lot of different people at different moments in time. You know, it's possible for someone or some group new, to come in and pick things up. And one example of that is the GRASS GIS, which I'll run through in a second. We talked about the development cycle in open source being one that's more decentralized. Not to say that there's no kind of coordination, but the management of projects can be in the hands of a steering committee. And we'll talk about one organization, OSGIO, in a second, that facilitates that kind of work. Here's just a table of examples of different applications, platforms, operating systems with a free and open source versus a proprietary equivalent. One note, I mentioned that open source applications typically get a lot more updates. So you might see in version numbers more periods, more kind of indices to mark that change. So there's a convention about how to read those. Moving from left to right, there's kind of a major version, a minor version, and then a patch or a super minor version. So the first or leftmost digit connotes deep functional change, new paradigms, or broken backward compatibility. So sometimes if you had a workflow, kind of a series of steps that you're trying to accomplish in your work, that you established and became familiar with in an earlier version, an earlier major version, you might have issues or problems trying to implement the same workflow in a more recent major version of that application. And it's true that, you know, you can have issues with a minor version or a patch too, but they're just less likely. Fewer things were altered, and so there's less likely that any of those alterations leads to a problem for your particular use case. So that second digit denotes changes in functionality. When that happens, the third version is going to be set back to 0. So that's a good thing to note with the major as well. When a number changes to the left, the digits to its right, I'm having a tough time highlighting those, just those, will also be reset to 0. And often you'll see for the third digit, smaller software patches. So bug fixes, minor tweaks. A quick note on the programming language that underlies different open source applications. These could be different from one another. So typically written in C or C#, Java, maybe .NET. Just some examples of desktop packages, GRASS, which now you'll see incorporated into QGIS, written in C, a few others written in Java.NET. So these are the source codes for those applications. So I mentioned GRASS GIS for a second as an open source project that has had different groups spearheading or leading, coordinating its development over the past 40 years. Oh, that's interesting. I'm just seeing this data. I wonder if they've had an anniversary this year. Began in the U.S. Army. So the Construction Engineering Research Lab, picked up after a period of dormancy by Baylor University in Texas, and then in 2001, taken over by an Italian research center. Now, most of the use of GRASS wouldn't be as a standalone application, but rather through its implementation in Quantum GIS. And these are just some of the examples within GRASS of what's potential, what's possible. Often, or initially developed for the use of raster GIS, so this being kind of continuous data where the structure is a grid with a number of rows and a number of columns divided into cells, each of which has a value. Initially, that was what GRASS was used for, but now often can be used for vector analysis. Vector being a different geospatial data structure where the objects are points, lines, polygons that all have a coordinate in a shared coordinate system for reference of location. So Quantum GIS, this is perhaps the best parallel to the Esri suite of products, initially resembling ArcGIS for desktop, but taking on some of the data organization characteristics that would later be implemented ArcGIS Pro. And so that'll be when we download QGIS and work in it, that is what should be kind of the most familiar to you. Here's an example of the older layout, just so you see it, this being more closely related to ArcGIS Desktop. You can see the version of 1.4. I believe it's 3.20 something now. So it's come a long ways, and that's in the capabilities, but also the layout. It still has a kind of a standard GIS table of contents to the left, tools at the top, layout, but maybe a few differences with kind of tabs to the right as well, making it easier to access some of the functions. Map window, I'll skip some of these. There are other examples of projects that maybe don't have as much as wide usage, but you know, maybe it helps to see the name. GDAL and Ogre, so these are libraries, pre-written code that can be accessed for reading, writing, and processing. And so they're associated with different data types. GDAL with raster, which I mentioned is the gridded data, each cell in which has a value. Ogre for vector, and they're both acronyms here: Geospatial Data Abstraction Library, OpenGIS Simple Feature Reference. These, I believe the base code is C, but they're accessible as Python libraries too. Easy access within QGIS, and actually within Esri products too. You don't see it, but it's there. So these are Ogre here at base is tools for manipulating vector data. So if you want to calculate a buffer, if you want to look at details about the data, if you want to project vector data from one spatial reference system, a coordinate system, to another, you can use Ogre. GDAL, tools for manipulating raster data. So this might also include kind of raster algebra. If you want to multiply every cell value by 2, if you want to convert between different file formats, so JPEG image, an NV raster, an ERDAS raster. This allows you to do so. There are certain command line utilities here. You don't have to access it within QGIS. It just may be easier to do so. Oh, on the subject of coordinate systems, there's PROJ4. So this is an engine for reprojecting and transforming geospatial data sets from one SRS, that's a spatial reference system, to another. So this is incorporated in QGIS, in Google Earth, in Esri products. It's one of those examples of the usefulness of open source. There's spatial reference systems might be, as I mentioned, geographical, where they make reference to position on the surface of a round or nearly spherical Earth, versus projected coordinate systems, where location is in 2 dimensions, and we're talking about a projected surface from the Earth to a flat plane. There are kind of a few different mathematical ways to transform the location of points from one to another. And kind of the need to do so is based around trying to limit or minimize inaccuracy in properties such as shape, feature size, distance, and area within your particular area of interest. So it's kind of a fundamental need for spatial analysis, but it's one that is kind of governed by not easy to do, but relatively simple mathematical processes. Certain standards here are these EPSG codes. There's a unique code for every spatial reference system. Well-known text. This is a text markup language for representing spatial reference systems. So where you can type out whether it's a few characters or a string of a few lines to communicate the fundamental characteristics of spatial reference systems. So this being kind of an open standard for use in things like a PRJ file or within a geodatabase in the Esri formats. I mentioned briefly OSGIO, so this open source geospatial foundation, formed in 2006, so not immediately after the kind of concept arose, but a few years later, and maybe when it became clear that there's going to be a need for a coordinating organization for many of these different projects in order to ensure that they keep going, that the people who are driving them, pushing them, or the institutions don't have kind of changes in their circumstance that lead to a project falling by the wayside. Different examples of projects. And one of the things that OSGIO does is they host in person, maybe they've done remote lately, a conference called FOSS4G. And that's free and open source software for geospatial. It's an annual conference, kind of a global community. A lot of these locations that I've looked up are North America, Europe. So here I have the location, some sort of a picture, and attendance numbers. So early conferences before OSGIO was formalized in kind of St. Paul, Minnesota, Ottawa, Canada, looking at a few hundred people. Expanding, so into Europe, South Africa in 2008. So expanding the reach, Sydney, Australia, 2009 here. Also expanding the attendance. So this kind of going from 500 to 400 to 800. It's not exactly linear, but you see kind of Denver, Colorado, 900, Nottingham, UK, 2013, 800. I checked the attendance for 2009 in Bucharest, and this was a little over 1,000. So you can see growth in maybe the first decade of these conferences from just a couple hundred to nearly 1,000, and then there's been maybe a little bit of saturation. So I don't know how attractive Bucharest is as a location, how easy it is for people to get there, And this is in 2019, so I tried to step around kind of before COVID. But when we talk about a decentralized development process, a community of developers, which is maybe a good parallel for people who are going to go to an international conference on these projects, things like QGIS, open standards, open data. It's about 1,000 people who can swing it in any given year. So maybe people go every other year. I don't know. I don't know their lives. But it's decentralized community, but it's not limitless. Some of the language that you hear, or that you see, I should say, when used to describe open source development is that it's democratic. It democratizes it. And it kind of does, I guess, if people vote with their time. But there are upper limits on it. And hopefully with more users, there's more interest in development, further engagement with the projects. But it's not a it's not as revolutionizing as perhaps some of the language suggests. A different model, better in some respects, and maybe more difficult in others. So a summary of those. So open source GIS is fun. It's a rising force still. I think the adoption of these applications is becoming greater. Weaknesses of it, possibly cartography, making maps. Although, as we'll see with web maps, that's one area where open source applications were pioneers and continue to underlie some of the most widely used applications. And also, I guess there's just the time investment. So having to learn different softwares and workflows. With some of the proprietary commercial platforms, for instance, Esri's ARC suite of products, once you kind of are into that, you're in. When you're in, you're in. Not to say that everything is easy in ARC Pro, for example, but there are people whose job it is to help you, to point you to kind of the next steps in your workflow. So that could be data collection, could be data processing, analysis, publication. So working within the same suite of products from one manufacturer kind of can ease kind of the transition in that regard. Strengths of open source are the flexibility. So the ability to read, write different formats. You're not locked into a kind of a single proprietary model. Rather, there's more interoperability. And also maybe more flexibility in how you can engage with it. So you don't need to kind of go, if you love working in some aspect of a workflow, you don't need to kind of change your job. It's something that you can make potentially small contributions to within a community. Again, there's an economic gain by not having to pay license fees. As students of GIS, you can buy limited term licenses of a lot of proprietary software at affordable prices, but that becomes less the case when you're no longer a student. And you're no longer, again, dependent on those proprietary vendors, on their schedule for bug fixes, on their willingness to fix something. Some bugs don't get fixed very quickly. Some features simply don't get added. And I'll wrap it up there.